There's an old but potentially dangerous game called the Salt and Ice Challenge. My take on it, don't take it. It's not worth it. You can get permanently damaged from this, and it's very, very painful. Check out this story from a couple of TV stations in Ohio.
Liza Danver is live at Kettering Medical Center with details on why a sixth grader and her mom are issuing a warning tonight. Liza.
And doctors here at Kettering Medical Center say since the start of summer, they've seen more than one child a month come here to the ER.
The ice is freezing on.
The end result could be a painful red mark or blisters, the equivalent of a second-degree burn.
They're not seeing the long-term consequences that we're seeing in the emergency room. They don't get that this can cause scarring, can cause blisters.
For 12-year-old Kerrigan Claywan of Troy, the dare gave her frostbite.
I didn't really think that it would hurt me.
There's a lot of chemistry in this salt and ice challenge, but it's also why salt and ice, along with a little water, is used to freeze homemade ice cream in a homemade ice cream freezer. It's a bit more deep than we usually get into in high school chemistry, but part of it we do get into, and that's what this lesson is about. Dissolving one substance in another lowers the freezing temperature. It also happens that it raises the boiling temperature. And here's the way cool chemistry part of this behavior. Like so much in nature, it follows a pattern. If it follows a pattern, we can figure out that pattern with math, and with math, we can make predictions. Okay, so let's take a look at a problem like this. What are the boiling and freezing temperatures? Let's take a look at a problem like this. What are the boiling and freezing temperatures of a solution that contains 118 grams of calcium chloride and 846 grams of water? Well, it turns out that calculating boiling point and freezing point change uses virtually the same equation. The equation is delta T, that's the change in temperature, times I, we'll discuss I and what it means later. Essentially, it's the number of ions that any chemical breaks up into. And if it doesn't break up into any ions, then I is equal to 1. You can basically ignore it because multiplying by 1 gives you the same thing anyway. Then it's multiplying times a constant, then times the mole concentration, which we discussed in our last lesson. Let's break this down now. If we're doing a change in freezing temperature, so some change in temperature of freezing, then I is not going to change. It's going to be the same. We're going to have a constant for freezing, and the molality doesn't change. If we're talking about the change in boiling temperature, okay, we're going to use a small letter B for that. I is the same. The only thing that's different here is there's a constant for boiling, or the boiling temperature, and then times the molality, which is always going to be the same. If you have the same amount of solute, in this case calcium chloride, dissolved in solvent, in this case it's water, then the molality of the solution hasn't changed. So I is equal to the number of ions the solute breaks into. Now this goes back to, at least understanding this, is the same understanding you had when we were writing complete and net ionic equations, where whenever we had an ionic compound dissolved in water, it split up into separate ions. So we know the formula of calcium chloride. Calcium has a 2+ charge. Chlorine, when it's bonded in a binary compound like that, has a 1 negative charge. So that means we have 2 of those. 2+ and 2 1 negatives gives us a balanced compound. And when we put it in water, this is going to split up into separate ions of calcium and chlorine. There are 2 chloride ions here. Okay, so that means that I is 3. 1 calcium ion, 2 chloride ions. The total number of ions is what I is. I equals 3. Okay, so we figured out what this is already. We just need to know what Kf is. And Kf and Kb are both found in your test references. Here's Kb for H2O, 0.512 Kelvin kilograms per mole. And for the change in freezing temperature, K is 1.86 Kelvin kilograms per mole. So we've got those numbers already. We've got to find the molality. Remember, molality is the moles of solute over kilograms of solvent. So we have 118 grams of calcium chloride. We've got to convert that into moles. So calcium's atomic mass, we look up on our periodic table, it's right here, 40.08. Chlorine's atomic mass is 35.45. In the formula for calcium chloride, we've got 1 calcium and 2 chlorines, so times 1 and times 2. So we're going to have 40.08, and multiply this times 2. I believe that comes out to be 70.90. Add those together, we get 98 on the end over here, and that's 110.98 grams of calcium chloride equals 1 mole of calcium chloride. Whenever we calculate the molar mass in my class, that's what I expect, is that you're going to write this equality statement when you're done. So if we have 118 grams of calcium chloride, you have to use all the significant digits because those tell you how precise the measurement was to start with. We need it. Put that over 1. Use this equality statement to write a conversion unit. Grams go on the bottom here. So 110.98 grams of calcium chloride. The moles go on the top. So the result is that this fraction, because these two things are equal, this fraction actually equals 1. We multiply all this together, divide, multiply and divide. The resulting number we get is going to be the same amount of calcium chloride as we started with. We're just changing it from grams to moles. In our problem, we have 5 significant digits and 5 significant digits. So we want 5 significant digits here in our final answer. We're going to underline the insignificant digits, 1, 2, 3, 4, 5. So everything after that is insignificant. Draw an arrow to show how we're rounding off. And we have 1.0633. This 5 makes the 2 round up, or causes the 2 to be rounded up to 3 moles of calcium chloride. So we know the number of moles of calcium chloride now. And that's going to go on the top of our molality. You know the kilograms of solvent. We were given the solvent mass in grams. We just have to convert that into kilograms. So 846.00 grams of H2O. Put that over 1. We know that there are 1,000 grams in 1 kilogram, and this is an absolute relationship, 1,000 grams in 1 kilogram. So we're not going to use this for significant digits, but we're going to put the 1,000 grams at the bottom because we want to match the units of measurement here on the top and bottom. Put 1 kilogram on the top. We do the math, we get 0.84600 kilograms of H2O. These grams are going to cancel, leaving us with kilograms, and that's the dimensional analysis part that's so important. Now, if you're not sure how to do that in your head, you can just put in 846.00 and divide by 1,000 and hit enter, and we can see we get 846. But the only thing is, you have to know this had 5 significant digits. The answer needs to have 5 significant digits. The calculator doesn't show you 5. It only shows you 3 significant digits. All right, so let's see. We have the top and bottom of this. Now we've got moles per kilogram. So the molality of our solution is going to be 1.0633 moles of calcium chloride for every 0.84600 kilograms of H2O. And this is part of the math we did yesterday in the homework. And so we want to find out what our molality is. And we take 1.0633 and divide it by 0.84600. And I get a molality then that is 1.256855799196. Kind of round it off to 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 5 significant digits. 1, 2, 3, 4, 5. Those are insignificant digits. This is going to be moles per kilogram of calcium chloride dissolved in water. So we don't have to list the solvent here if it is water. It's assumed to be water. But that moles per kilogram is the molality. I'm going to round that off now to 1.256, and the 5 causes this to round up to a 9. Since moles per kilogram is molality, we can just write a lowercase m here, calcium chloride solution. All right, so this is the solution. All right, so we've got the molality. We can look up the Kf and Kb. We now know what I is. Okay, we look up the Kf and the Kb. We know what I is. We can plug everything in to find the change in temperature for boiling and freezing. Okay, so let's see. Let's start with this one. The change in the temperature of freezing is equal to I. We said I is 3, so it's 3 times Kf. We look up on our test preferences. It's right here, 1.86, 1.86. And we write this in this fashion. We have a negative 1 exponent on the moles. It comes out to be Kelvin times kilograms over moles. Okay? So Kelvin, kilograms, moles inverse means moles go on the bottom of the fraction. All right, now our molality then in our equation here, the m, is this we calculated, and that's 1.2569 molal. All right? And molal, remember, is moles per kilogram. And that's going to allow us to cancel these units of measurement. So look how this works out. Kilograms cancel, moles cancel, we're left with temperature, and we're looking for a change in temperature here. Okay, let's do the math. So we've got 3 times, tilt it up so you can see it maybe, 3 times 1.86 times 1.2569, enter, and I'm getting a change in freezing temperature of 7.013501, O2, and what we have left is Kelvin. Okay, that's our unit of measurement. Now, a couple things to point out. This 3 here was a counting number. Recall that we counted the number of ions here to get I equals 3. 1 calcium, 2 chlorides, that's the number of ions, I equals 3. So that's an absolute value. It's not like you can round things off to only 1 digit here because of this number 3. Those counting numbers like that are infinitely significant, so we ignore that when figuring out the significant digits for our final answer. This number has been calculated, and this number we know we calculated it. So of these two numbers, we want to look at all the measured and calculated numbers, and of these two calculated numbers, this one has the least digits, so our final answer needs to have that same number of digits. So we want 1, 2, 3 significant digits, underline everything else, draw the arrow to show that we're rounding off, and we get 7.01 Kelvin is our change in temperature. The only thing you need to remember here is that freezing temperatures always go down and boiling temperatures always go up. So this means that the temperature of freezing for this solution is going down by this many Kelvin units. Now, the change in temperature, for whether it's freezing or whether it's boiling doesn't matter, the change in the temperature of freezing or boiling is always final temperature minus initial temperature. initial temperature is the temperature of freezing for the solvent without anything dissolved in it. Our solvent, remember, is water, and you should know the freezing temperature of freezing for water is 0.00 degrees C. And since the way you get the Kelvin temperatures to add 273.15 to that, then it should be easy to see, I hope, that the temperature of freezing for water is also 273.15 K. So we have the initial temperature. The initial temperature is always the freezing temperature of the solvent without anything dissolved in it, the pure solvent. Our change in temperature is this many Kelvin units down, so it's a negative number. We've got negative 7.01 K equals final temperature minus initial temperature, which we said was 273.15. And the way we're going to isolate our unknown here, since this is addition now, or subtraction, is we're going to add 273.15 to this, and whatever we do to this side, we must do to this side, plus 273.15. Add that to both sides. Well, this one goes away, so we end up with nothing but final temperature on this side. Okay? When we add these two together, what we essentially are doing is subtracting. Since we have a positive number and a negative number, we've got 273.15, and we're going to subtract 7.01 from that, and we get 266.14. 266.14 K. And that's what we're looking for. That's our final temperature of freezing. Okay? Well, what about boiling? The only real difference is boiling goes up, and we're going to have a different K. So the K for boiling is a different number. Okay? Just about everything else in this equation is the same. And when we get to the final calculation, we're going to add instead of subtract. Let's do that. So our temperature for boiling is going to change. I is going to be the same because we're breaking up into the same number of 3 ions. We need to find the correct K for boiling, and that's on your test references. K for boiling is 0.512 Kelvin kilograms per mole. 0.512 Kelvin kilograms per mole. The molality didn't change. It's exactly the same. 1.2569 moles per kilogram. So moles cancel and kilograms cancel. So this is the change in boiling temperature in Kelvin. We have 3 significant digits here. 1, 2, 3, 4, 5 here. This number is a counting number because we counted the number of ions, so it's infinitely significant. We ignore it for figuring out significant digits. So we want 3 significant digits because it's the same number of digits as the measured or calculated number. Both these are calculated numbers. The measured or calculated number in the problem with the least digits. 1, 2, 3 digits. Underline, draw an arrow. And our change in boiling temperature is 1.93 Kelvin. Now, the change in temperature is always the final temperature minus the initial temperature. The initial temperature for this kind of calculation is always the boiling temperature, or if it's the freezing temperature, it's the freezing temperature of the pure solvent. So the freezing temp or the boiling temperature in this case of water, since that's our solvent, the boiling temperature of water you should know is 100.0 degrees C, and we'll say 00 degrees C. In Kelvin, that would be 273.15 plus this, and so that's 373.15 K. I put C over here. This should be K for Kelvin. So then, the change in temperature is 1.93 0.93K. The final temperature for the solution is what we're trying to find. Initial temperature is the temperature of boiling for the pure solvent. That's 373.15K. To find final temperature, we need to subtract, or really add both sides, this number to both sides. So we're going to add 373.15K. That's going to get rid of that. That's going to be 0 here. So we'll have final temperature plus 0, which basically is final temperature. So that pretty much goes away. And we're going to add whatever we do to this side of the equality statement, we must do to the other side. So we're going to add 373.15 to this side. So let's see, that's 8, 10, 5, 375, 375.08K. And so that's our final temperature for the solution when we add the amount of solute to the solvent. So some things to remember now. Change of temperature for freezing and change of temperature for boiling are the same equation. It's I, which is the number of ions that whatever the substance is that it breaks up into. So soluble ionic substances, you just count the number of ions. Anything else, I is going to equal 1, times K, whichever K it is, it's either freezing or boiling, times the moles per kilogram, mole concentration. So these are the same equations. We're just changing whether it's boiling or freezing. Okay? Remember, boiling temperatures change, always go up. Change in boiling temperature always goes up. Change in freezing temperature always goes down as you add more solute to the solvent. Then we've got the change in temperature. Regardless of which boiling or freezing you've got, the change in temperature is always final temperature minus initial temperature. And with those equations, you should be able to solve any of these kinds of problems about the change in temperature that occurs whenever you add solute to solvent. The couple things that you need to know, and these are not really new things, just things that we've dealt with quite a bit already, is that the freezing temperature of water, temperature of freezing for water, is something you should memorize, 0.00 degrees C, which is also 273.15 K, and the temperature of boiling for water is 100 degrees C, which is 373.15 K, or Kelvin. So here's a homework problem for you to try. Ethylene glycol is the main ingredient in antifreeze. Its formula is HOCH2CH2OH. Based on what you learned in the nomenclature unit, this chemical could be named ethane 1,2-diol. If 25.25 grams of ethylene glycol is dissolved in 100 grams of water, what would the freezing temperature become? And one little hint for you, ethylene glycol is not an ionic compound, so it doesn't split up into ions when it dissolves in water.